Shook it up. I never loved nobody fully. Always one foot on the ground. And by protecting my heart truly, I got lost in the sounds I hear in my mind. All of these voices I hear in my mind. All of these words I hear in my mind. All of this music, and it breaks my heart. And it breaks my heart. And it breaks my heart. When it breaks my heart. Suppose I never ever met you. Suppose we never fell in love. Suppose I never ever let you kiss me so sweet and so soft. Suppose I never ever saw you. Suppose you never ever called. Suppose I kept on singing love songs just to break my own fall, just to break my fall, just to break my fall, just to break my fall, break my fall, break my fall. All my friends say that of course it's gonna get better, gonna get better, 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 better. I never loved nobody fully. Always one foot on the ground. And by protecting my heart truly, I got lost in the sounds I hear in my mind. All of these voices I hear in my mind. All of these words I hear in my mind. All of this music, and it breaks my heart. And it breaks my heart. I hear in my mind. All of these voices I hear in my mind. All of these words I hear in my mind. All of this music, and it breaks my heart. And it breaks my heart. And it breaks my heart. When it breaks my heart. When it breaks my heart.
All right, so continuing from last time, we were looking at algorithms and algorithm analysis, and we set the necessary groundwork for setting up a framework by which we can describe algorithms using pseudocode. And then, of course, we introduced this 5-step process of algorithm analysis where we identify the input size, the elementary operation. We determine how many times the operation is executed with respect to the input size. And then finally, we provide a big asymptotic analysis of it. I wanted to focus on each one of these steps in detail, even though the first two seem like they're obvious, right? If you write good pseudocode, then you're already writing down what the input is. If you're writing good pseudocode, then you already have an idea of what the input size is. But there are subtle situations where it is not at all, it's not immediately obvious as to what those should be. So for example, identifying the input size, or identifying even the input, excuse me, right? Again, this is generally given as part of the pseudocode. If you write good pseudocode, it should be pretty straightforward. But in some cases, it may not be clear, right? For example, if there are multiple inputs, right? So let's take a look at an example that you might be familiar with already, linear search, right? So the idea here is that you're given a collection of things, and you need to search through it. What we did on Monday was we searched for, we did a linear search. We searched through the collection for the maximum value. Now what we're going to do is we're going to have an additional input here, right? My input is going to be a collection of elements, and I'm going to name it A, A1, A2, dot, 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 AN, and a key element, right? And I'll call it K here, right? Now it's not entirely obvious that what the input should be because you've got two things here, right? You've got a collection and then you've got a key. Let's go ahead and go with the rest of the algorithm and describe it, and then we'll come back to this first step here. All right, my output is going to be an element. Note unelement, right? Not necessarily the first element, not necessarily the maximum element, not necessarily the last element, whatever. Unelement A in A, such that A is equal to K. Now again, a reminder on what good pseudocode here is, right? Did I say that this was an array? Nope. Did I say that this is a list, a map, a set? Nope. I'm just saying a collection. I'm keeping this as general and generic as possible because I want this to apply to any language, not just any type, right? So it's polymorphism with respect to the entire language itself. I did label these A1 through AN. Does anybody notice anything weird about that, right? From a computer science perspective? From a mathematical perspective, certainly not. 1, 2, 3, all the way up to N. But from a computer science perspective, do we begin our indexing at 1? Not generally. But this is pseudocode, so that's what I'm going to do. And then finally a key K. Did I say that these were integers? So that I would say that if A sub I is equal to K, right? Nope, that's code. Right? Unelement A such that A is equal to K. Here I am using equals in the algebraic term. The thing on the left-hand side is equal to the thing on the right-hand side. Okay? Let's go ahead and implement this algorithm. For each A in A, right, if A is equal to K, then we found our needle in the haystack, and we output A. Note here that I am not returning, right? I am not throwing an exception. I'm not returning a value because this is an algorithm. It's not a function. It's not a method. I'm going to use the same tricks that I did yesterday to indicate my blocks. A vertical line along with this little thing at the bottom here, okay? What should I do if I don't find my needle in the haystack? In other words, if I get through every single thing in the entire collection here and I never find something that matches K, it's an unsuccessful search. What should I return? Should I throw an exception? Should I return null, right? Output null? Well, do all languages use null? Those coming from a Python background, do you have null in Python? Nope. What do you have? None, right? Or none type, right? Those coming from a C background, do you have lowercase null in C? Nope. What is it in C? It's all uppercase. Right? But there is a concept of null in any programming language. I'm going to put in a mathematical expression here, phi. That will be my placeholder. And as long as you put it up here in your documentation in your input-output expectations, then it's perfectly fine. Phi if no such element. There we go. All right. So now let's go ahead and focus on that first step where we identify the input. The input, if we just went with what's written down here, there are two inputs, A and K. But now, are both of these necessarily relevant? Right? Which one of these is more relevant? The collection that can grow in size and that could be 1 billion elements versus 10 million elements versus 5 elements? Or the key, of which there's only ever one thing? Right? It's probably going to be the collection here. Why? Because my algorithm is iterating over that collection. If there are 100 elements in this collection, then it does 100 operations. If there are 1 billion elements in this operation, in this collection, then it's doing 1 billion operations. Right? So when given multiple inputs, right, choose the one choose the one that is most relevant to the behavior of the algorithm. Right? Another example would be Euclid's GCD algorithm. Right? And we're not going to go over the algorithm in detail, but hopefully you've seen GCD before, greatest common divisor, right? And in that one, there would be two inputs, right? Given two integers, A and B, right? Output their greatest common divisor, right? All right, I'm not going to go over the math or anything like that, but I'm given two inputs here, A and B. So how do I simplify this, right? Without loss of generality, W log, if you've ever seen that in mathematics, right? Without loss of generality, assume that A is greater than or equal to B. There we go. That allows you to winnow it down to just one input, right? i.e. the input size of A is at least as big as B, and so only focus on A. Why is this okay? Why can we do this without loss of generality? If it's not the case, if B is bigger than A, what are you going to do? Just swap them, right? And now this assumption holds, right? They could be equal, of course, in which case you don't need to swap them. In fact, the actual algorithm itself will actually end up swapping them anyway in the first iteration in favor of the smaller one, right? So, without loss of generality, focus on one input, right? In general, only focus on one input if there are several, right? Some more standard examples, right? Examples, a collection is usually better than a single value or item, right? GCD algorithm, et cetera, et cetera. So in other words, what you want to do is you want to make your life simpler, right? You want to analyze this algorithm with respect to one input and one input only. If it's got three, inputs, 4 inputs, or 5 inputs, whatever, right? Focus on the one that's most relevant. And then do these tricks of, okay, well, these both look relevant. What am I going to do? I'm going to go ahead and focus on one without loss of generality. Here's my reasoning for that. Okay. The second part, identify the input size. Right? Again, let's go back over here to, all right, so I'll say the collection. Oops. The collection A. So, step 2, what's the input size, at least in this case? Let me go ahead and number these, 1, 2, 3, 4. Well, also, that's encoded in part of the input. By choosing n here, what have I done? I've made my life easier, right? The size or cardinality of A. And in this case, I have a variable for it, n. Right? Why are we using n, by the way? We'll understand this later on in more detail, but have you ever, what does n kind of connote? Or what does n kind of communicate to you? Usually what we do is we'll write these things down as time functions, right? T stands for time here. If you were to think about x, what does x kind of tell you? X, y axis? And what values can you have on the x, y, and axis? Well, you could have 1, you could have 2, you could have 3.14, you could have you could have 3.7 or something like that. You could have negative values, -7 over here, right? Do those sound like input sizes to you? Can you have an array of 3.14 elements or 3.5 elements? Nope. So, no. Can you have an array of negative size? No. So what are we really focusing on here? We're focusing on positive values, right? In other words, nothing over here. And we're only focusing on integer values, 1, 2, 3, 4, ... Right? In other words, those things are called the natural numbers, right? 0, 1, 2, 3. You can have an input of size 0, right? An empty list, an empty set, an empty array. So that does make sense. But it doesn't make sense to have something that is 1.5 elements. And that's why we use n, because it's the natural numbers, right? You might have seen this misnamed as the counting numbers, right? Where you don't have 0 or something like that, but no, These are the natural numbers, and they do include 0. Okay? All right, so the size or the cardinality. That's pretty straightforward. Sometimes it's not, right? It's subtle, but it's important and can be tricky. If you have something straightforward like a collection, it's simply the size, the number of elements in that collection. What about if your input is, say, a matrix? Right? So let's come over here and visualize that. And I'm going to get rid of all this. I don't need it. So you might not have done any matrix operations, but you've probably at least seen matrices before, right? You could have a matrix that's 4, 7, 8, 3, 9, 2, 4, 9, 7, 1, 0, 4, right? There's a matrix. It's got rows and it's got columns. How big is this matrix? It's 4 by 3. Oops. 4 by 3. Now, in general, you could have a matrix that is simply just n by m. So what's the input size here? Let's visualize it again. Let's go ahead and get rid of all this. What if I have a matrix that's n rows and m columns? How many entries are there? Number of entries are going to be n times m. So you could say that the input size is n times m. That gets confusing though. Now we've got two variables. Instead of a nice function, like a time function here that we're going to have in n, now it's going to be a time function in n comma m. That's, I don't like having to think about two variables. Do you? No. All right, so let's do that trick again, where we make a valid assumption, a reasonable assumption, right? Without loss of generality, suppose that n is greater than or equal to m, right? That means that what's the bigger side here? This. And so we could say that the input size is at most n times n. Why? Because m is less than n, so m times n is less than or equal to n times n. And we have a nice compact way of writing that, right? Oops. N squared. But you can go even further. Okay, well, so what? What I'll do is I'll just go ahead and assume that that one row is my input or something like that. I could simplify this to say n, where I introduce yet another variable here. And now my time function is going to be a nice little compact thing where I've got a different value. I don't have that square. I don't have two variables. I don't have that square sitting out there. I just have this new value right here, this big N. Okay? You could also simplify it so just N. Right? That's a reasonable assumption too. Why? Because whatever analysis you eventually come up with, all you have to do is multiply it by N, and you're good to go. Right? You can simplify the analysis and then in the end, make an adjustment if you really want it. Okay? So without loss of generality, we can assume that n is greater than n and only consider n, or n squared, or just another variable which is a placeholder for n squared. Okay? Here's yet another tricky one. What about that Euclid GCD algorithm? What if the input is a number, like say an integer? What's the input size there then? Right? And this is why I focus on each one of these steps in detail, because it gives us an opportunity to review some math. Right? So, if I write down a number, say I'm trying to compute the GCD of A is equal to 1,738, right? And then some other number there, I don't even care what it is, right? What is the input size of A? Would you say that it was 1,738? Not really. It didn't take me 1,738 characters to write down that number, did it? No. So what is the input size here? The number of characters, the number of digits necessary to write it down. 4. If I had a different A, 1,743,842. I'm just making these up, right? Would you say that the input size is larger? Yeah, but it's not 1,000,000 times larger or 1,000 times larger. What is it? The number of things that, number of digits required to write this down is 7. So in general, how many digits are required to represent, in other words, write down an integer? A. Right? So how many? It took me 4 here. It took me 7 here. How do I figure that out? So let's work backwards. Let's derive this. Right? What if I gave you a certain number of digits? Right? So number of digits. If I gave you 1 digit, what is the maximum value that you can represent with that 1 digit? 3, 4, 5, 6, 7, 8, 9, 10. 10, how many digits does that require? 2. So what was the maximum value? 9. What if I gave you, what if I gave you 2 digits? What's the maximum value that you can represent now? 99, okay. 3, 999. What if I gave you k digits? What's the maximum value that you can represent now? What's the pattern here? 10 to the k minus 1. Now why is it minus 1? Because you have to start at 0, right? Otherwise this is 10 to the third, 1,000 minus 1. This is 10 squared minus 1. This is 10 to the first minus 1. Right? Let's keep going. What if I gave you, what if I worked on the other side here? What if I just had a number a, right? How many digits are required to represent that number now? Right? All you need to do is say, all right, well, a is equal to, at most, 10 to the k minus 1, right? Less than or equal to. Let's suppose that it is equal because that's when it maximizes the number of digits. There we go. Okay. Now the answer that I want over here is k, right? In other words, I want to solve for k. Well, one part of that is easy. A plus 1 is equal to 10 to the k. Now what do I do with that k, or that 10 to the k to get rid of, to isolate k? So what's that function called? Log. Log of what base? 10 of a plus 1 is equal to k. So in other words, what's my answer? Log base 10 of a plus 1. Right? Forget about that plus 1, who cares? Let's do the exact same thing, but with respect to a computer. Why did I just do that in base 10? Because we are humans and we have 10 fingers and 10 toes. Right? So what if I gave you bits instead? Number of bits. And by the way, the original name for bits was bidget, right? Binary digit. And then it sounded weird, so they just shortened it to bit. Right? What if I gave you 1 bit? What is the maximum value that you can represent in binary? Well, here it's going to be 1, which in decimal is equal to 1. If I gave you 2 bits, then you would set them both to be 1. Anybody know what that is in binary? All right, 3. Right? If I gave you 3 bits, 1, 2, 3, 7. If I gave you 4 bits, 1, 1, 1, 1, that's going to be 15. Do you start to see a pattern here? If I gave you ... k bits, right, k ones, what value is that going to be? What's the pattern here? Think powers of 2. This is 2 to the first, right? Or 2 to the, 2 to the first. This is 2 to the second minus 1. This is 2 to the third minus 1, 8 minus 1. This is 2 to the 4th minus 1. And so in general, it's going to be 2 to the k minus 1. Looks almost exactly like this. What's the only difference? The base. Right? So to work backwards here, if I had a, it would not be log base 10. It would be log base 2 of a plus 1. Right? Or roughly about log of a. Now what have I done here? First of all, I've ignored this little plus 1 there. Who cares? Right? Roughly. That's what I'm looking for here. Because at the end of the day, on step 5, I'm going to ignore these lower order constants anyway. Okay? What have I done here? Have I explicitly written the base like I did here or here? Nope. We're computer scientists. What are our bases? It's always implicit that it's base 2. Okay, why? Because computer science. We're doing everything in binary here. There's no such thing, well, there is such thing as an analog computer, but it's not common. Right? This contrasts with, say, a self-respecting mathematician. A mathematician, what base would they use? What base is the natural log? The natural log. If I were to write this base out explicitly, what is that base right there? E. E is about 2.171 ... whatever it was. Right? What the heck is natural about 2.71? Right? Well, let's think about these in the other terms. Base 10, that makes sense. 10 symbols in the digit system, right? 0 through 9. Binary, that makes sense because there are 2 symbols in binary, 0 and 1. Is there any number system where there are 2.71 symbols? 0, 1, and something that is a fraction of something? No, right? At least not something that we can conceive of, but we can theoretically think about it. Right? So why would a mathematician consider this natural? Those of you with Calc 1, tell me about e to the x, and tell me what happens when you take the derivative of e to the x. It stays the same. It actually doesn't stay the same. What it actually does is it has a natural log of e out front with an e to the x up there. But natural log of e, what happens to it? It goes away. And therefore, we're left with e to the x. It is the base value such that the first derivative has a coefficient of 1. What if you were to take 2 to the x and take its first derivative? You'd have to look it up. Don't worry. It's natural log of 2 out front, and then it doesn't change either. Right? But this isn't 1. And so mathematicians don't like it. Right? It would be 10 if it were 10 to the x. Right? Mathematicians don't like that. Mathematicians like it when these little annoying constants disappear out front. Right? That's why it's natural. Okay? All right, so there's our answer. It's the number of bits required, right? It is the number of bits required to represent that number. Why did I just take 15 minutes to explain this? It's because it's important. Let's look at an example of where it is super important. Right? Here's a classic example of, this is not exactly the sieve of Eratosthenes, but it's really, really close. Right? What I want to do is I want to find a factor. So given an integer, x, is it prime or composite? Right? So for example, prime numbers, 2, 3, 5, 7. You all know prime numbers. What else? 11, 13, 17, ... Right? 8 is not prime. Why? Because 2 divides it. Right? That symbol means 2 divides 8. Okay? So how do we test whether or not something is prime or not? What's an easy way of doing it? What's a straightforward way of doing this? What if I had 1,731? Right? Well, how would you go about testing this to see if it's prime? Brute forcing it. Well, first of all, is it divisible by 2? No, it's certainly not even. Is it divisible by 3? It is. Darn it, I didn't mean for it to do that. All right. 5, 6, 7. There we go. And is it still divisible by 3? Darn it. I think it is. Okay. 9. There. Now it's not divisible by 3, I think. Right? All right. Question mark. Right? 4. Would I have to test 4 again? No, I already tested 2. And if it's not divisible by 2, it's certainly not divisible by 4. I would then test 5. Is it divisible by 5? No. Right? Because it doesn't end in 5 or 0. Divided by 7, ... Right? Eventually you get down to the last value that you need to test for it. Do you need to go all the way to 1,739? No. Because if you've got a prime factor up here, then somewhere in the middle, that has a corresponding prime factor up here. Okay? So what is this middle right here? Square root of n. All right? You only have to test up to the square root of the number, or x, sorry, I was using x. Okay? So let's go ahead and write an algorithm to do this. Our input, again, more practice here writing pseudocode. My input is going to be an integer, and I'll go ahead and call it n here to make it confusing intentionally, and then we'll fix it. Right? My output is going to be prime if n is prime, composite otherwise. Right? Now, there are some, corner cases, 0, for example, that's even, but it's not prime, it's not composite either, right? Because it's not divisible by anything. 1 is technically not prime or composite either, right? But we'll go ahead and consider an integer n greater than or equal to 2. There, that solves our problem, right? All right, so I'm just going to go ahead and iterate through every single prime. For each prime p from 2 up to the square root of n, oops, don't want to make it look like Python, if p divides n, then output composite. Why? Because you found a prime factor. If you get through every single prime from 2 up to the square root of n, and you don't find any prime factors, what do? Output prime. Right? Excellent. That is kind of like a sieve of Eratosthenes, where you just brute force it and try everything. So how many times does this algorithm operate? Well, it operates at most what? At most, oops. At most, come on. I don't know why it went thick there, right? At most, the for loop operates square root of n times. So if I'm looking inside this loop here, I'm looking at this division as my, my elementary operation, right? And it executes at most n square root of n times. Hey, that's better than linear. Right? In other words, n, right? Because square root of n is smaller than n, right? And certainly if we had a way of enumerating primes efficiently from 2 up to square root of n, then we could get away with even less work. Right? Because we're not going to test 4, 8, right, 10 if we've already tested their prime factors. So this is an upper bound. It's going to be, we're going to say that it's square root of n better than linear. Implement it. Just try it sometime. The simple sieve of Eratosthenes. Then try it on a really, really large prime number. You will be waiting, literally, you will be waiting for the heat death of the known universe in order for it to compute. Why? Because we did something wrong here. Our input was n. But what was our input size? We just went through that, right? What's our input size? It should be log of n, right? Log of n. With that in mind, tell me what this thing really behaves like. Square root of n is equal to Let's give this another name, big N. That's our true input size right there. Now solve for little n in terms of big N. Right? 2 to little n is equal to what? Oops. It's going to be equal to base 2 implicit, 2 to the big N. And so what is the square root of little n? It's the square root of 2 to the big N. Does that look better than linear to you? Anytime you have something raised to a power, right, what is that thing called? It's not a linear function, it's not a quadratic function, it's not even a polynomial function. What is this function called? Well, what was e a placeholder for? E to the x, right? What does e stand for? It's just the letter that they chose at random. No, what does it stand for? Exponential. Right? Really, really, really slow. Right? So this thing really does matter. You have to identify the correct input and the correct input size. The third step here is identifying an elementary operation. Right? Ultimately, we only want to focus on one operation. So for example, let's come back over here and look at linear search. What happened to my linear search? There it is, right? Now, if you were to actually program this in, say, C or Java or something like that, then you have to write out a for loop. For I equals 1, I is less than n, I plus plus. I just counted there 3 different operations: an initialization, an assignment, a comparison to see if you should still keep going with that for loop, and plus plus. You're adding 1. So addition, comparison, and an assignment. Okay. I only want to focus on one thing, not 3 things. Look inside of that for loop there. You're doing something else, right? You're outputting things, maybe, right? You are doing another comparison. So which one should you focus on here? Should you focus on what's necessary for the control structure of the algorithm, or should you focus on what the algorithm actually does? I'm going to focus on what the algorithm actually does. Yes, you do have some work here. If you were to program this on a computer, you would have a bunch of different operations. In yesterday's class, they pointed out to me that to do this in assembly would require 4 instructions to even determine whether or not, I is less than or equal to n, right? And each one of those instructions is an instruction on the CPU, right? Each one of them takes a certain amount of milliseconds or nanoseconds or something. Those are important engineering concerns. We're not looking at it from an engineering perspective. We're looking at it from a mathematical perspective. So we focus on what's inside the loop. Should I consider this? It doesn't always happen. In fact, it only happens ever once, and that's the end of the algorithm, right? I'm going to focus on this, the most common or the most expensive operation, right? So generally, you focus on the most expensive, or the most common, or the most relevant, right, operation. There's not one answer that I can give you, right? For example, when we look at sorting algorithms, we'll look at, say, comparisons. You could also look at swaps, right? If you were wanted to be memory efficient, you might focus on those swaps, because that's a memory operation. If you wanted to make sure that it was time efficient, you would focus on comparisons, or maybe something else that was a little bit more expensive. You're just going to get a different analysis at the end of the day, right? Depending on what you focus on. There are some obvious wrong answers, but there might be several correct answers, okay? But what you do not do is you do not consider operations necessary for the control structure of the algorithm, right? Because those are going to be proportional to whatever's inside of a loop. Some common examples, of course, would be the ones that we just looked at, comparisons, right? Arithmetic operations, such as additions, subtractions, or multiplications and divisions. Why did I group those 2 things together? Additions and subtractions. Is there really any difference between those 2 things? 10, or plus negative 10 is equal to subtraction of 10, right? So just negate your value and then add it, and you're doing additions instead of subtractions, right? What about multiplications and divisions? A times B is, or A divided by B is what? A times 1 over B, the reciprocal. Right? So those two operations are essentially the same from an efficiency point of view. As we've already seen from linked lists, traversing a linked list to get where you need to be, that's your node, that's your elementary operation. That's the most relevant thing with respect to the original demo that I showed on Monday. Right? Okay, so that takes us through the first 3 steps here. Identify the input size, the input size, and the elementary operation. Once you've identified those 3 things, now here comes the actual math part, where you have to determine how many times the elementary operation is executed with respect to the input size. Let's take a look at linear search again here. So the size or cardinality. What was my elementary operation? lm op. It's the comparison. And this is why I'll number my lines, because I'm going to say line 2. Right? Now, how many times is this executed with respect to the input size? Careful. Right? What if you got lucky? Best case. What's the best case scenario here? You're looking for a needle in the haystack. Guess what? You found it the very first place that you looked. How many comparisons did you make? 1. 1 comparison. You find it, A1 is equal to your key. Right? Done. What's the worst case? Right. One of the worst cases is where you find it at the very end, right? The last thing that you're looking for, right? You're searching for your keys now. And where is it? Well, it's the last place you look. Why? Because you're done. You found it, right? Or you don't find them at all, right? Your keys have gone missing and they're gone forever. Right? How many comparisons did you make in either case? N comparisons. Right? So I wrote this one up here and I wrote this one down here. And I left a big gap. Why do you think I left a gap? Can you always assume the worst? Or can you always assume the worst? Can you always assume the best? Probably not. Another way of looking at this would be what? An average case. Now, a naive way of doing this is to simply take the worst case plus the best case and simply average them, right? And you would get that this is about n divided by 2. Right. A more rigorous mathematical analysis would involve a lot more steps, a probability distribution on successful key comparisons, then a summation, and then solving that summation into a closed form. But guess what? You end up with the exact same answer as the naive way of doing it. Right? So we're not going to do it. Is there any difference between this and this? There's a 1/2 out front, right? I'm going to go ahead and get rid of all this. Right. So let's graph it. Right. What does n look like? What does this one look like? If instead of, again, I'm not doing the x-axis, I'm doing the n-axis. What does a linear function look like? A nice, smooth curve of, move it down, there, that looks good. Right? That's n. Right? Now again, why am I not focusing on the other 3 quadrants? Because this is an input size. There's no such thing as a negative input size. There's no such thing as negative time either. You run a computer and you get an answer 10 days ago? Nope. That's time travel. It's not possible yet. Right? What about 1/2 n? What would it look like? Somewhere in there. Right. So now put on your calc hats for a second here and tell me, is there really any difference between these two? The slope here is 1. The slope here is 1/2. If you put on your calc hats, calculus hats, right? How do you determine the rate of growth of functions? You take the first derivative. So let's take the first derivative of n. That's really easy. What is that? 1. In other words, a constant. Right? What if I had 1/2 n, oops, and I took its derivative? 1/2, guess what? Also a constant. In other words, is the rate of growth of these two things any different? No. Right? So that's why it doesn't really matter. Average case, worst case. We're going to focus on the worst case in general then. Right? Why? Because you can't always assume the best. You can't always assume the worst. So maybe you want to look at an average case, but we are going to assume the worst. Because what I want is an upper bound. If I run this program, I want a guarantee that it will execute within 5 minutes or something, right? I don't want to just, flip a coin or throw the dice and, okay, it might execute on average in 5 minutes, but there's that one input that it's going to go ahead and take centuries or decades or something like that. Right? I'm going to focus on the worst case. What's the worst case here? As we've already said, n, right? N number of comparisons. Because you get to the end of the line and you find it, or you get to the end of the line and you found out that it doesn't exist. Okay? That's going to be my worst case scenario. All right? Okay. And again, there is a slope here, there is a slope here, but again, engineering. You bring in new hardware that's twice as fast. You upgrade to that 4080 Ti, right? What happens to this constant sitting out front here? It gets even smaller, right? Because there's another constant sitting out in front here, c, indicating how many seconds does it actually take to make a comparison. Right? Doesn't matter then. If there's another constant sitting out front there, it doesn't matter if your constant is 1 or 1/2. They're the same thing. Okay? Yeah.
Would then the quote-unquote y-axis just be Cn, or how many?
This is Tn, so time. Or memory, or Reese power, or whatever, right? But for us, it's just going to be T for time. Okay? All right, so there's your elementary operation. We don't have enough time here but to go over another example, but we'll do so on Friday. Just to summarize here, you need to analyze the elementary operation, how many times it's computed with respect to the input size n. And so that gives you a resource function. This answers your question here. What am I mapping from and what am I mapping to? I'm only using non-negative input values, right? You can't have an array of 3.5 elements. You can't have a number of 3.5 bits, right? Everything in computer science is discrete. Many of you are taking discrete mathematics right now. What do we mean by discrete? Either finite or enumerable. Right? In other words, there are 5 bits. There's no such thing as 5.5 bits. Right? There's 5.5 bits, then up to 6. We only are interested in monotone functions. In other words, not something that goes down. Can you imagine an algorithm that gets faster and faster as the input size increases? That doesn't make any sense. It is also no time travel. There's no negative values. So this real value here is real positive, right? Input sizes to a resource measure such as time. It doesn't take you negative 10 seconds to run this program. That doesn't make any sense. It may require some art, may require summations and solving summations, other calculations, finding closed forms. We'll get a lot of practice doing that. In general, you want to assume the worst case scenario and provide an upper bound on your worst case running time. Because you are measuring a resource, time, memory, whatever, and you want an absolute upper bound on what it's going to take to get this algorithm to run. We'll do a lot more examples throughout on Friday and then into next week. Right? And then, of course, we still have step 5, characterizing using a big O analysis. All right, I'll see you on Friday then.